the backpropagation algorithm, right? So today, what I'd like to do is to kind of revisit that a little bit, and then we're actually going to implement our first neural network from scratch, and hopefully this will be an opportunity for you to kind of connect the dots between what you already learned from Professor Khan's lecture versus how things are done in practice. So does that sound good? All right. By the way, yesterday I mentioned, you guys could, define your own, machine learning model and then try to train it. How many of you were able to actually do that? All right, great. So, what we're gonna do today is not gonna be repetitive to anybody. All right, wonderful. Please go ahead and open up a browser, and then go to Colab. Again, colab.research.google.com. Oh, sorry, Zoom. Give me 1 second. All right. Okay, sorry about that. So, as usual, please go to the. Let me actually just put the URL over here in case you don't remember. HT, yeah, forget about HTTP. Collab.research.google.com is the address, and go ahead and visit collab.research.google.com. Log into your account, create a new notebook, and once you're done, import Torch. Now, none of you has done the homework. How dare you? I'll give you about 5 minutes to implement the following. Um, by the way, if I turn on the whiteboard, will the people on Zoom be able to see that? Okay. Well, here's the mission for today's class. I want you to implement, don't worry, it's very easy. I want you to implement a model that takes X as an input. So Fx equals to W times X plus B, where W is in our n by n, sorry, not n by n, but n by d, sorry, minor modification. Let's do it this way. So it's d by n. Pay attention to the right panel. The left one is a little geeky way of doing things. And then, X is obviously a d-dimensional vector. And we assume that X is a row vector. And then B, actually, you know what? Let's not be too ambitious. D by 1, how about that? And then B then is just a scalar. Cool. And then just for fun, we're going to add sigma to this, where sigma is the sigmoid function. Okay. So define model that takes X, and then this is what you need to implement. All right, you have roughly 5 minutes. Have you guys watched the Squid Game, the TV show, Netflix? Yeah, that's what's going to happen. Um, so concentrate. Yes. Yes. So to be this more clear, yes. If you don't want to implement sigmoid from scratch, there's a predefined sigmoid, torch.nn.sigmoid. So, you have about a couple minutes, but how many of you were able to get it done so far? No? All right. A couple more minutes. All right, time's up. Any success? Okay, one survivor. All right. Um, excuse me. Let's do this together. So um, the implementation of the model itself is actually pretty simple. So what you need to do is to just think about the individual operations. So what you're going to need is to multiply x with w, right? And we saw that the usual multiplication with the star is going to give you an element-wise multiplication, which is not the thing that we want to do over here, right? So what you got to do is x at, w to make it a matrix multiplication plus b, right, is what you need to produce at the first place, right? That's the first thing to do. And for the clarity of my code, I'm going to just declare a new variable called z, all right, which is, the terms inside of the parentheses. So far, so good. How many of you were able to do this? Oh, yeah, we'll get there. We'll get there. Now, after this, torch.nn.sigmoid is the name of the function that you can use. And maybe some of you were struggling with this one because the preferred usage of this is as follows. So for those of you who know Python pretty well, that function sigmoid is not actually a function. It's a function generator. So what it returns is another function that does sigmoid. So if you just directly put x inside of this, it's not going to work. But instead, you have to do this. And you can do it outside of the function. We're not doing object-oriented programming or anything. So, define sig like that, and then throw z into that, function. So sig is actually a function. It does look like a variable if you're from, C++ or Java background. Oh, sure. Thank you. Yes. Thank you. And then that is what we're supposed to compute, which is the value f, right? And then simply what you need to do is to return f. Now, obviously, in order to define this function, we need two variables, w and b. X, we're not concerned because X is something that the user is going to put in, right? But W and B is something that we need to define somewhere. So that kind of goes back to your question. So here I have W. And the simplest thing you can do is to, well, first of all, we need to define the dimension. So dimension D, for now, I'm going to set it to 2 dimension. Okay. D equals to 2. And then what I could do is to create a torch tensor with the dimension 2. That's it. And then B is, again, torch tensor. In this case, scalar, right? B is a scalar. Is the simplest implementation that I could, do to implement that simple model, which, by the way, is a perceptron, right? You still remember that. So that's that. Of course, in this case, PyTorch will just assign some garbage value, depending on what is already, in your memory, on your either GPU memory or CPU memory, and we don't want that. So to have a better control, actually, what I would prefer to do is to generate a normal random variable for W, and then I could do the same for B, but to be more fun, for this one, I'll just set it to 0. Doesn't matter. You can do rand-n as well, but this is what I'm going to do to add more variation. And voila, that's the definition of our model. So now that I have the model, what I can do is, for example, generate a random set of values. So again, I'm going to create a torch tensor, and then let's say, I initialize x with 1 and 2, and let's make sure that Python recognizes this as a floating point number. So I put the period over here, and then simply f equals to model parenthesis x, and print f is the prediction of my model. Okay. Of course, this prediction doesn't mean anything, obviously, right? Because the model was initialized with some random weights, so it's going to just produce some garbage, right? A random combination of the input values, but it does something, so that's a progress. So far, so good. Okay. Now that we have the model, here's what we're going to do. We're going to create our own synthetic data for classification. Okay. So our goal is to let the model F to return a value ranging between 0 and 1. So remember, sigmoid function, there's a cutoff and then saturation, right? So sigmoid returns the value between 0 and 1, right? So below certain threshold, everything will be cut off to 0, and then above certain threshold, will saturate to 1, right? So my model F is always going to return some value between 0 and 1. And our goal here is to have them return, those values ranging between 0 and 1 according to the class label, okay? So I'm going to synthetically generate some data points, and then we'll try to classify them. So to do that, let's declare a variable called dogs. Okay. And then the dogs, what I'm going to do is to do torch.rand-n, Gaussian random distribution. And what I am going to do is to create, let's say, 100 dogs. And those dogs, each of the dog has 2 features. Okay, that's our. So I'm just pretending we're dealing with some real data. It's not actually dogs. So, but it's let's assume that, let's pretend that we collected some features describing dogs, the animals, and then we have 100 of the animals, and then there are 2 features describing the dog, and then let's leave it like that. Cats, on the other hand, we're going to do the same thing, random distribution. To be fair, same number of cats, right, as dogs. And again, 2 features, right? But this time, let's say cats have slightly biased, values compared to the dogs. Okay. So to display what I mean by that, here is a useful thing to know. Plot lit, pyplot, that's PLT. So this is a Pythonic way of, plotting, graphs and charts. Again, very similar to MATLAB. So if you have experience with MATLAB, you should know what is going on. So plt.scatter is the function that draws a scatter plot. And what I'm going to do is to draw a two-dimensional scatter plot where the x components are filled with the dogs, the first component of the dogs. So remember that the column was a slicing operator. So all rows in the 0th column is what we're doing over here. And then for the y-axis, we're going to put dogs, 1, which means the second column, right? All rows. And then for the dogs, let's say red is the color that we're going to assign. Let's just give it a try. It's too big. So probably on your end, things will look okay, but since I kind of blew up my screen, so you don't have to type this. But this is one way of reducing the size of the figure. Much better. So that's the scatter plot of the dogs in that two-dimensional feature space, right? And then we're going to do the same thing for the cats. So copy the same line. Let's swap the name of the variable to cats. And then instead of red, we'll do blue. And voila. I have two Gaussian random distributions slightly off of each other. One thing I noticed just now is that this might be a little hard to classify because there's a lot of overlap. So, our goal, intuitively speaking, is to put a straight line over here because we're talking about perceptron. We're going to put a straight line over here to classify cats versus dogs. But maybe I created a problem that's a little too complicated, too difficult. So what about multiplying, say, 0.2 to each so that the standard deviation gets shrunken? Oh, this is too easy. Okay, how about 0.5? Oh yeah, there you go, perfect. All right, so we have two distributions, dogs and cats, right? And then our goal is to put a straight line. We're not going to be 100% accurate because there's some overlap between cats and dogs. So I'm making it a little more realistic, right? But, a good classifier, should put a line somewhere in between, in this region, right? So that we can, classify blue and red accordingly. So far, so good? All right. Now, we got to make the ground truth labels. So dog label is the variable to store the labels for the dogs. And for the dogs, I'm going to assign torch.zeros and then 100. Okay. So it's simply just the vector filled with zeros, right? And then cat label, on the other hand, is going to be excuse me, torch.ones, filled with hundreds of ones. Okay. So what that means is, we're gonna, because computers cannot understand like the human language, right? We cannot just call it dogs or cat, right? That's the human, understandable language, but that's not, favored by the computer. So instead, we're calling dogs 0 using the number, and we're calling the cats 1s, right? Um, and of course, rerunning the code will not change anything except the distribution a little bit. But after you're done with that, here's the important part that I wanted to follow very carefully. So now we have the two separate variables, dogs and cats, right? But we're going to concatenate them together. We're going to, merge them together into a single data set and then shuffle them up, okay? So that we cannot infer, which one is which just by the order, right? So to do that, torch.cat, don't be confused with the name of the animal this time. This is shorthand for concatenation. The concatenation means you're, connecting two vectors together or two tensors together. And what you could do is, put another parenthesis inside of that function, but do something like this. And then what's going to happen is, when you print the shape of the data, you're going to realize now we have 200 by 2 tensor. So if for dogs and cats, each of them were 100 by 2 tensors. Now by concatenating, nating them together, now we have 200 by 2, the full set. Same thing goes to the labels. So we're going to do torch.cat again. And then we have dog label OS. Okay, cat label, right? And then let's print shape of the labels. So now, again, dog label was simply just a 100-dimensional vector filled with zeros. Cat label was a 100-dimensional vector filled with zeros. Now that we concatenated them together, we have a giant 200-dimensional vector filled with zeros and ones, right? Half and half. All right? So far, so good? Yeah. So now that we have a consolidated data set, what we're going to do is to shuffle them around, okay? Because right now it's super easy because the first half of the data is dog and the later half of the data is cat. So, model might be just able to just simply guess by the ordering, right? So we don't want that. So what I'm going to do is to create a random index, and this might be a new function called random permutation. So permutation means ordering of numbers, and we're generating a random ordering of numbers that is, of the length 200. So what randperm is going to do, here, let me show you. Randperm is going to do is to generate, 200 numbers ranging from 0 to 200 and then shuffle them around. So you can see that those integers are all kind of mixed up. So our strategy is to use this new indices to shuffle the index of data and then shuffle the row index of the data. Does this syntax make sense? Yes? No? Gave up? Is the person good? Come on. Too tired? Hungry? All right. Well, I assume that the lack of reaction is maybe this is too easy for you guys. So, if you just print the labels, you will see that now the zeros and ones are all mixed up together. is initially, well, I forgot to actually show you what it looked like before, but initially we just concatenated zeros and ones. So like the first half was zero, the second half, half was one. Now after the shuffling, we have, all mixed up, labels like this. All right. If this makes sense so far, now this is where the fun begins. We are now going to train a neural network. Okay. So first of all, let's see what our model is currently capable of. So I'm going to throw that data into my model. And then whatever it spits out, I'm going to call it prediction. All right. And then my prediction at the moment looks kind of like this. It's all messy, right? And apparently, if I compare this, so let's say the first 10 predictions, I'm comparing that against the first 10 ground truth labels. 10 was a little too ambitious. Let's go with 5. Yeah. So 5 ground truth labels compared against the first 5 predictions. They don't line up very well, as you can see. Okay. One minor thing is, this was already covered in the theory lecture, but with the sigmoid, since we're returning values between zeros and ones, after making the prediction, we're going to assume that anything below 0.5 is 0, and anything above 0.5 is 1. So with that being said, this is 1, which is correct. This is 1, again correct. This is yet again 1, but this time incorrect. This is 1, correct. This is 0, correct. So it's 80% accuracy already. Because we have small samples, that's just a serendipity. And if you actually, to compute that actually, what you could do is to, first of all, threshold your predictions by doing this. So, greater than 0.5. And, this thing will convert the tensor into a Boolean tensor filled with true and false. And then I'm blinking on the name of the function, but I think you could do this as well. No? All right, sorry. Cast. Sorry, why am I blinking on this one? S type. As type. Let me cheat. PyTorch typecasting. Oh, 2. There we go. So dot 2. So for a given tensor, if you do dot 2, you can convert the data type. So initially, this whole thing inside of the parenthesis was a Boolean tensor. And then by doing dot 2, you can convert that data type into an integer. Or if you want, you could also do it a floating point number to match up with this. So let's say let's say actually, instead of predict, let's call them scores. And then this, after the conversion, I'm going to call it prediction. All right. Now, the error is defined as prediction minus labels torch dot absolute. Okay. And if I print the error, voila, this is what I get, right? So this error tensor is going to basically flag the locations where you got the error. So, of course, right now we're just visualizing the first 5 elements, but if you run a statistics on the error, so for example, torch dot mean is a function to compute the average of a tensor elements, and I can do something like this. Okay, so this is going to give me a mean absolute error, which is in this case the same as the accuracy percentage, right? So for the entire 200 data points, it's surprisingly accurate. The error rate is 25.5%. Okay. Which is fine. All right. So we're gonna we just established a baseline. By the way, this number can be different because we're all generating random numbers. So the random numbers that you guys generated and I generated might be different. So the actual details might be a little different here, but that doesn't matter. We just established a baseline, and then we'll see if we can improve this. So far, so good. Any questions? Yes. You can do uniform distribution. Then your figure may look a little more squarely. The Gaussian distribution looks more round. Uniform, you'll have different shape of the distribution, but doesn't really matter. So yeah, feel free to experiment with the uniform distribution or some other distributions. That's totally fine. Other questions? Yes. Yes. That's what's coming. But before we get there, any questions so far? All good? All right. Now, what I would like you guys to do is to create a for loop. So I'm going to create a for loop, and this is a Python way of creating a for loop. So let's just go with 10 epochs. Epoch is iteration. For some reason, neural network community uses the term epoch. And our goal here is for each of the epoch, we want to make the prediction of scores. All right. And then define the loss using that score by comparing scores with the ground truth. And then for no reason, I'm using mean squared error. So torch dot mean of the square error is what I'm going to use, but feel free to use something else such as mean absolute error, or if you want to be, more adventurous, then there are many other, loss functions that are available, such as cross entropy. But for simplicity, let's just go with mean square error. So again, I computed the difference between what the model spit out versus the ground truth label. I squared them, the difference, and then just computed the mean. And that's how I define the loss, right? And all we got to do is to call loss dot backward. Remember that? Yeah. So this is how you do the back propagation. And we're back propagating from the loss function. Down to where? What are the gradients we're interested in evaluating? Gradients of the data or gradients of the W? Gradients of W and B. Who said that? Yes. Good. All right. So W dot grad and B dot grad, those are the things that we're interested in. Was there a question? So W dot grad and B dot grad are the things that we're interested in evaluating. And the good news is you don't have to do any, you don't need to do anything because loss dot backward will already calculate all the gradients for you, save it to W dot grad and B dot grad. Except that I forgot to, require grad for W and B. Remember that? So if you don't require grad explicitly, then PyTorch will just assume that you don't need a gradient, and then when it constructs a computational graph, it's not gonna do anything about it. So you have to explicitly say, hey, I'm gonna need a gradient for both W and B by calling these two lines. Now PyTorch knows that, this guy's trying to compute the W gradient and the B gradient. All right. So that's really it. And the gradient descent algorithm, right, is nothing more than updating the entries of W and the entries of B, right, by subtracting them by the amount of the gradient, right? Of course, if you do this, this might be a little numerically unstable. So here I'm going to define a learning rate, and I would guess 0.001. It's always good to start with some, reasonably small number to be safe. And I have no idea how that will work out. So we're going to start from there and then, modify it later on, right? But this is essentially how gradient descent is implemented. So far, so good? Yeah. And that's really it. We're going to print the epoch number and the loss value. And since we're interested in just one value of that scalar tensor, this is how you access the value of the scalar tensor. PyTorch is a little bit messy in terms of the syntax design. So if you're coming from this nice, NumPy, syntax, this might be, a little awkward, but hey, that's what it is. Oh, and the important thing is, after epoch, you have to set the gradient to 0. You have to reset the gradient to 0. Otherwise, remember my, diagram of the back propagation, there were, bins, slots where you save the numbers, right? If you don't wipe it out, it's gonna just accumulate numbers over there so that your gradient calculation may not be accurate. So um, you want to call w.grad.0 underscore and b.grad.0 underscore, which is the function to wipe out the values and set everything to 0. So we're resetting the gradient. I rarely comment my code, which is a bad habit, but reset gradients. Let me just call it that there are residues from the previous calculation that will be remaining in the memory, which will just mess up, the calculation of your previous gradient computation. For the details, I can explain to you after the class. Now, if you're able to follow up to this point, feel free to go ahead and run the code and see how the loss value changes over the number of epochs. So in my case, I started from 0.1727, and then it went down to 2.6, 2.6, still 2.6. So it's kind of slow, right? So maybe I was too conservative about the learning rate. So how about I make it 10 times more aggressive? Now I get to 2.0. Let me see if I can push it further by making it 10 times bigger. Wow. All right, this is much more promising. And then, of course, 10 epochs was not probably sufficient, so I'm going to increase it to 100 epochs. So I'm training it longer. And seems like I'm able to push down the loss value to 0.13. Okay. So I'm going to give you a couple minutes to kind of pause and ponder and compare your code with my code, try to run your code, and then, mess around with the learning rate. Excuse me. Mess around with the loss function, and then see, how far you can, reduce down the loss value. Also, feel free to experiment with, excuse me, feel free to experiment with the number of epochs. So like 1,000 epochs. It's not gonna take a while. See, it's only 1 second. And then, you can reduce the loss further down. So I'm gonna give you about a couple minutes to, compare your code against mine, and try to absorb and, understand what's going on. All right. And in the meantime, if you have any questions, please feel free to ask. Yes. Yes. For those details, we're going to talk about it in the next session. Today, since we're talking about essentially a linear classifier, there's no worry of overfitting at all. You can never overfit a linear classifier because it's a straight line, right? There's no degree of freedom. So today, we're not going to worry about it. The most important thing for today is to understand this workflow. And then in the next session, we're going to be talking about how to babysit the training process by monitoring the overfitting, how to, fine tune the hyperparameters more systematically, and so on and so forth. So we'll get there in the next session. Today, just, try to absorb, and make sure that you have a solid understanding how, backpropagation works. All right. Yes. Yes. So PyTorch tensor, that's a great question. PyTorch tensor is an object that is comprised of many entries, and W dot data is where the actual data is stored, as opposed to, for example, W dot grad is where the gradient is stored. So if you don't do this, so maybe your question is, why would you do that instead of this, right? If you do that, then you will mess up not only the actual values of W, but also the gradient, which is the thing that you don't want to do. Okay, so that's why we're specifying that. Hey, we're modifying only the data. Yeah, yeah. Oh, so that's not the same. Yeah, yeah. Is that good now or okay? Yeah, that's the whole point of the training process. You repetitively show the same set of data, and then each time you show the data, the same set of data, you modify the model slightly, a little by little, and then as we repeat that process over and over again, we converge to a better model. It's like the human learning process. Like you never master a subject by reading just one book, right? You have to read a book, you have to listen to a lecture, you have to, program yourself, you have to watch YouTube videos, you have to ask ChatGPT, whatever you have to do, right? You have to repetitively see the same material over and over, again, so that your brain's kind of, fine tuned, towards that knowledge, right? So yes and no. Because we're talking about a linear classifier, even with like 10 samples, you should be able to train it. Yes, up to the point where it is impossible to gain any additional improvement, right? So that's the minimum, optimum. All right. Other questions or some interesting observation about your code or my code? Yes. Yeah, no, there's no golden rule or anything. You have to empirically determine what's the best. And again, we're gonna revisit that in the next session. By the way, what time do we end? Oh, 2 minutes. Okay. Well, all right. So assuming that you all were able to train your model, let me just show you one more thing, which is the evaluation of the accuracy. So for that, what I'm gonna do is to basically just copy this code over here. I'm gonna copy this and then go all the way down and paste here in the new cell. So again, using that same data, I'm gonna produce the scores, and then the score value is greater than 0.5. We're gonna consider it as a prediction of 1, right? And then anything below 0.5, we're going to consider it as a prediction of 0. And then this is how we compute the prediction error. So in my case, I started from 25% error rate, now down to 14.5% error rate. Again, that exact value might be different across the board. Also, I could have, changed the learning rate and then, change the number of epochs and, further optimize the code. But seems like this is what I get, from the current setting of the learning rate and the current setting of the everything else. All right. For the interest of time, I might just do a cooking show where I just put a pre-made So here's, briefly speaking, here's a way of visualizing the data. So the first thing is the scatter plot, right? We're putting data, in a scatter plot, and then the color of each of the point will be based on the label. And then the second one is, I'm not going to bother to explain this, but is to draw a straight line. And then all I did was to compute the slope and then the y-intercept from the w values and the b values. Okay, so the details, I think you guys are smart enough to be able to, our labels plural. I think you guys are smart enough to be able to compute the y-intercept and the b-intercept. Y-intercept and the slope. But that, let's make the line more visible. Black. Maybe let's make the figure a little smaller. Again, no worries. Don't worry about the syntax over there. So as you can see, after the training is done, I have the black line over here, and then you can see that it does a fairly good job of splitting red and blue, right? Although, because of the limitation of a linear model and then the complexity of the data itself, we're unable to perfectly split red and blue, but I'm pretty happy with the result. So with that, in the next class, we are going to revisit some of the things that we talked about today during Professor Khanna's class, especially about convolutional neural networks. And then we'll also talk about how to babysit the training process and, all the specific details in terms of how you design a neural network architecture. So right now, all we can do at the moment is to design a super simple perceptron model. But, in the next class tomorrow and then maybe, on Friday, we're going to see how to actually, assemble those building blocks, assemble the perceptrons and convolution layers to design something much cooler. And then I'm going to show you some, more advanced way and simpler way actually to implement the gradient descent and the training loop. Actually, what you saw today is a harder way. And I intentionally did that because you need to understand what's going on. In fact, the whole gradient descent can be just done by calling optimizer.step. You don't actually have to, do any of those. But it's important for you to understand not the result, but this part of the code. Yeah. So I hope you were able to take notes of this at least. And if something doesn't make sense, I know it's a lot of information, right? Every day, just pouring information. So I don't want you to drink from the fire hose. So take a moment to look at the code, and then the best way to learn machine learning and all this practical stuff is by doing. Get your hand dirty. So we started with the perceptron, but you already know the theory of multi-layer perceptron. So try to convert this into a multi-layer perceptron and see if you can do a better job of classifying the data. Or you can, I mean, now that you have the code, you can change the data distribution by making it harder, easier, right? And see how you can, yeah. So any, whatever question you may have, go ahead and do it. Any change you make to the code is not gonna burn your computer, right? It's not gonna burn Google's computer. It's not gonna harm anybody. So feel free to do crazy things like changing the learning rate to 1 million or whatever, right? And see what happens. And let the code to fail, right? That's the best way to learn all this practical stuff. So, and you're not damaging anything. You're not harming anybody. So feel free to do it, and that's the best way to learn. So with that, thank you so much, and I'll see you guys tomorrow.